nothing is going to change.
I don't think Aphrodite is really there. Like I heard some people don't have it, but
Pleasure to invite Siddharth Chandak to give a talk. He's currently a PhD. So Siddharth Chandak is currently a PhD candidate in EE at Stanford University. He received a BTech from IIT Bombay, where he was awarded the PGM and gold medal. And his research includes game theory, multi-agent systems, stochastic approximation, and applications of reinforcement learning.
Thank you, Professor Narayanan, for hosting me. So, my talk today is learning to control unknown multi-agent systems. This is in collaboration with Professor Westfield and Bambos from Tel Aviv and Stanford University, respectively. So, this is how the talk will go. So, first, I will talk about general game control, what I mean by controlling a game. Then I will give a specific game which we will focus on for most of the talk, the strongly monotone games. And then I will discuss two scenarios. The first one is where the manager controls some linear coefficients, and the application, the algorithm there is based on 2 times scale stochastic approximation. And then I will give another scenario of game control where there is a discrete set of parameters that the manager controls, and we will discuss a bandit based algorithm for that, slight variation of the standard stochastic bandits called equilibrium bandits. So this is the overall outline. So let's start. What are multi-agent systems? Anything which has multiple agents is a multi-agent system. They interact with one another, they play some actions, they get some utilities. The examples could be robots playing football, bunch of autonomous vehicles traveling from one place to another, or a network of sensors, as in Internet of Things. How do we want to study them? We want to study them through games. So each agent is a game, each agent is a player, sorry, and each player takes some action Xn, and the utility of that player N depends on the action taken by all the players. So for example, in the autonomous vehicle scenario, the agents or the players are the vehicles, the action is the route they decide to take, and the utility could be anything, fuel consumption or time taken to travel that route. And hence, it falls under the formulation of a game. But what does each player want to do? They all have their own utilities, as we discussed, and all of them want to maximize it. There is a constraint of limited feedback, which could look like this. For example, the bandit feedback, where each player is playing some action x1, x2, x3. They don't know anything about the system. All they observe is the utility they receive back. That's it. Okay, so that's general game theory standard. Where does the control aspect come in? There is a game manager. They control some parameter of the game. It could be, for example, it could be the action set of the players, or it could be the utilities. We will mostly focus on the latter in this talk. But why do they want to control the players? They have some global objective which may not align with what the players want. So each player is optimizing for their own local objective, as we discussed, and the manager is optimizing for the global objective under, again, bandit feedback. So this is how the whole system will look. The manager decides some game control parameter theta. The players observe their utilities depending on the respective theta, and the manager only observes the global objective as feedback. The manager does not know the player's actions. The manager knows nothing about the system. Only the feedback is the global objective.
he doesn't know human utility also.
No, the manager knows nothing.
Wait, how is it different from manager being one of the players?
You could treat it as a Stackelberg game as well. Yes, it's just the applications we consider. The control, the manager control aspect is a bit easier to get intuition. But it's a Stackelberg game where the manager is the leader, everyone else is the follower. Yes.
And phi is additive? It's true.
Phi could be anything.
Any function.
Yes. I mean, we will, so the specific scenarios we discuss, we will take assumptions on phi and we will work with specific phi, but in general, it could be anything.
The players, do they know P, U1, U2, U3? What do they know?
The players in the general setup only know the reward.
Only the value. They don't even know the function.
They don't know the function. No. We will, for the applications we consider, they will not, as I get to them, I will talk about them, but about the scenarios, but they just don't know the utility, but they know the gradient of the utility for simplicity. But even if they know just the utility, they can compute the gradient using zero order optimization, single or 2-point estimator methods. But for simplicity, we will consider that they know the gradient. But okay. So this is a general game control setup. Hard to say much about it without specifying something more. So how do players update their actions? Do they converge to Nash equilibrium or do they rotate or something? To specify these, we focus on a class of games known as strongly monotone games. So strongly monotone games, a very nice class of continuous action games where there is a unique pure Nash equilibrium, and each player, if they just perform gradient ascent on their own utility, will eventually converge to the Nash equilibrium. But not just that, even stronger, intuitively they are the multi-agent equivalent of a strongly convex or a strongly concave function. So not just convergence but exponentially fast convergence in the absence of noise. So to define them, suppose each player is choosing some action xn in a convex compact set. We define this concatenated gradient operator, which is just nothing else stacking all the gradients in a vector. And then we have this definition that the inner product of y minus x and g of y minus g of x is negative and is lower than negative mu. If you are familiar with strongly monotone functions, this is basically saying that the function negative of g is a strongly monotone function. Okay, so as I said, a very nice class of games, because if each player just takes, updates their actions in the direction of the gradient, like this, they will converge to the unique pure Nash equilibrium, which is defined in the standard unilateral deviation way that no player can benefit by deviating from the Nash equilibrium, by unilaterally deviating from the Nash. Great. Is this what we want? Not always. So the Nash equilibrium is not always desirable. There are standard, the Brazes paradox is a very famous example of that. I won't talk about it because I will talk about the next one. Operational issues which are often observed in resource allocation game. So as I move forward, everything I say I will try to relate with the resource allocation game so that you get intuition and also see why the assumptions are justified. So what is the resource allocation?
One question. So for any application you have in mind, how do you actually design utility which satisfies these properties?
No, we don't design the utilities. We use standard utilities which are observed. For example, applications of like examples of resource allocation games include power control in a wireless channel. So there is a standard utility which everyone is using.
Yes.
Another example is power grids.
So previous definition. Yeah. So is it natural that they all satisfy this?
In this case, yes. That's why we work with them. Yes. So what are resource allocation games? As the name says, we are allocating resources. Not we, in a distributed manner, resources are being allocated. So suppose there are k resources and each player's action is a k-dimensional vector denoting how much of each resource they are using. Example could be electricity grids where the resources would be the time of the day. Wireless channels, the resource would be each channel, how much power they are using to transmit. It is often observed empirically that a few resources are heavily used. For example, in this example, R2 is being heavily used, creating pressure on the system. Intuitively, this could be like afternoon in a hot summer day. Everyone wants to use power at that time, but we want to incentivize them to spread out their power use. So how would a controlled strongly monotone game look like? The utilities, instead of given by un of x, they are now un of x theta. Players are updating their action as before, but just theta appears. And for a fixed theta, players will converge to the Nash equilibrium x star of theta. So what this means is that for a fixed theta, the game is a strongly monotone game. So this is the actual problem statement. How does the how does the manager learn what theta t to use such that the players eventually converge to a desirable Nash equilibrium under limited feedback?
But is the question easier if there is no noise?
The answer is is the question easier if there is no noise? Yes, significantly. I mean, it varies from problem to problem, but I will talk about the noiseless case as well.
Sorry, so is this not a so this game resource allocation game, is it not a strongly
It is a strongly monotone game.
but strongly monotone games have a unique Nash?
Yes, for each theta.
For each theta, right? So that's where the control part comes in. So the first scenario, controllable linear coefficient. So each player again takes action in a compact and convex set. The compact and convex set is going to be important later on, but so just remember that each player is taking action in a compact and convex set. They are not taking action in RT but a compact set. The utility now is given by two terms, the Rn of x and a linear shift. So Rn of x you can think of as an underlying original game, the reward coming from that. And the second term is the linear shift, which the manager is able to control. So as I said, this linear term is what the manager controls. So this beta that you see, if you stack them all up, the ND-dimensional vector is the parameter theta. What is n? N is the number of players, and what is d? D is the dimensions of the number of dimensions in each player's actions. So ND-dimensional vector beta is what the manager is controlling. In this specific setting, we are working with steering the player's Nash equilibrium towards a point which satisfies a set of k linear constraints. And again, banded feedback manager only observes the constraint violation, nothing else. This should have been AXT, but yeah, so the manager only observes the constraint violation, nothing else. Let's see why this AX equals L star problem has some meaning, and we will do that in the resource allocation setting. The constraints are just that each resource the total amount of each resource used should be equal to some constant Li star. In this specific setting, the manager could have just set the beta I for each resource, and that would have basically been a price or a subsidy. So if the beta was positive, then it's a price of using that resource, or if it was negative, then it's a subsidy or a discount. So this thing that we are seeing can be thought of as the betas can be thought of as price or subsidy in the resource allocation setting. In general, it could mean anything, but so let's quickly look at the assumptions. So the main assumption is that this Rn of x, the original underlying game, is a strongly monotone game. So if you define the concatenated gradients for the R functions, then they also satisfy the strongly monotone property. And if they satisfy the strongly monotone property, the gradient operator for the controlled game is nothing but f of x minus beta, because this term gives rise to f of x, this term gives rise to beta.
So is this are the beta playing the role of some kind of
Yes, they are basically that. Yes. And this implies that the control game is also strongly monotone, so nice to control. The mapping is Lipschitz continuous. The players observe noisy version of the gradient. The noise is standard martingale noise bounded second moment, and we also assume that the Slater's condition holds, so that the point is actually feasible. So this is the algorithm. So just the simple part, the key points are the manager broadcast alpha t. Alpha t, we will come to that. Alpha t is the actual Lagrange multiplier that you were talking about. and the manager observes the violation and updates the input. Each player basically does the gradient step in the direction of the gradient, and this beta that we talked about is directly related to alpha in this form. Remember that we need to take the Euclidean projection into Xn because we are working with a convex compact.
Capital M. This final update is a capital.
Oh, the martingale.
Okay.
So, better way to understand this would be using the vectorized form. And in that, you can see that we are subtracting minus A transpose alpha t, and the alpha t's are updated in this way. Instead of directly transmitting beta t, which can be a huge vector, nd dimensional, the manager is only transmitting an k dimensional vector, which is much smaller. So the communication is not very heavy. And this is basically just an iterative approach to solving the constraint optimization problem, a 2-time scale method to solving that using Lagrange multipliers.
Why is beta t needed to be transmitted? It's incorporated in the utility itself. Right? So if I get xt, I just get the subtraction value as my.
It depends on how you formulate the problem. One way to formulate it is since it's an additional price, it is changing at every turn, it has to be conveyed to the users in some way. So yeah, but it's a yes. If you model it that they are directly able to observe
The way you define ut of xt comma theta.
yeah, in that if you formulate it that way, then you don't need to send them additional.
All this martingale difference noise?
Oh yeah. Sorry, this is martingale difference
Yes,
noise.
yes, yes, yes.
The standard martingale difference noise it means 0. Yeah. So yes, sorry. This is the algorithm. The 2 iterations which are running, and this is basically a 2 time scale stochastic approximation, where the faster time scale is players updating their actions, and the slower time scale is the manager updating its input. So the timescales are dictated by these step sizes, eta t and epsilon t. They have to satisfy some properties, but the main point is eta t is larger, and hence this is a faster timescale. Epsilon t is smaller, so this is a slower timescale. The intuition for 2 timescale iterations is the faster one is so fast that it views alpha t as constant, and xt are able to converge to x star of alpha t. And the slower one is so slow that xt can basically be thought of as x star of alpha t. So even though the manager is actually only observing xt, it is in a way able to approximate what the violation at Nash equilibrium would have been, and hence it is able to steer the players in the right direction.
Is there no trade-off for this? Can it be increased?
Yes, we will talk when we in the next. Yes, so okay, we will discuss that. So start.
Does something go wrong in the same scale?
In this setting, yes. Yes. Yes.
You don't get convergence.
Yes. Possibly you won't get convergence. So this is the key assumption which dictates how the step sizes are, how the timescales are separated. Epsilon t square by eta t cube less than equal to 1, which basically says how slow the slower timescale has to be. The result is let's define n opt as the set of alphas which are nice, basically where we want to converge to. Our alpha t will converge to this set, our xt will converge to x star of alpha t, and the result of these two statements is that axt will converge to L star. Nice, the convergence part is easier. The finite time bound is you get O of eta t plus 1 by t epsilon t. There is a reason why eta t shows up like this and epsilon t shows up in the denominator. We will talk about it. But the best rate based on this result, I am not saying it's the best rate in general, is t power minus 1 by 4 plus some delta. It can be arbitrarily small. So nearly 1 by t power 1 by 4 is the rate of convergence. Let's try to understand the analysis in some detail. We won't go into much detail, but okay, recall that this was the 2-time iteration, right? The first key step is just rewriting it as fixed point iterations because they are usually easier to analyze. So I define small f and small g in a way such that this becomes f minus x and g minus alpha. So just adding and subtracting xt, adding and subtracting alpha t, nothing else. And this omega t that you see, which wasn't there before, is just the equilibrium noise. How far the xt are from x star of alpha t. So the very standard steps in a 2-time scale analysis, but basically writing them as fixed point iterations. Great. A property of strongly monotone games that the operator f is strongly monotone, which implies that this f that we defined is a contractive mapping. Contractive mapping is norm of f of x1 minus f of x2 is less than equal to lambda times x1 minus x2 for some lambda less than 1. But slightly disappointing that g of alpha is non-expansive. It is not contractive. It is non-expansive. Non-expansive is basically Lipschitz with Lipschitz constant 1. Why is this disappointing?
Sorry, what is G?
G was the fixed point mapping that I made for the flow time. So why is this disappointing? 2-time scale iterations, in general, iterations in stochastic approximation have been widely studied under the contractive assumption because they show up in reinforcement learning in a lot of places. But 2-time scale with a faster and with a contractive in the faster and non-expansive in the slower had not been studied before. So that requires some novel analysis which combines the analysis for 2-time scale iterations and the analysis for stochastic fixed point iterations with non-expansive mappings. But this is all the analysis part. The main thing is that it leads to a slower decay rate. But why did we get non-expansive mappings in the first place? That is because of the projection in the faster time scale. So as I asked you all to remember that the player's actions are in a convex and compact set, and that leads to a projection, and that projection leads to the non-expansive mapping. In the absence of the projection, both timescales would have had a contractive mapping, and we would have achieved a rate of O of 1 by t as in a recent work. But the main point is that projection into the convex and compact set, which usually has no effect on the steps, no effect on the convergence rate. In this case, brings down the convergence rate from 1 by k to 1 by k power 1 by 4. So, yeah. Any questions about the first scenario?
Yeah, a quick question. So, you also show lower bound that this is.
I don't have a lower one. No, I don't. Yes.
Is it important that the underlying function is a game, even if it's like one user inside and one user outside? All of this still.
Yes. Yeah.
So it's just that want to build the story, so you're putting a game inside.
I mean, if you look at it from a theoretician point, yes, it is just a story for it. But if you look at it from the application side, this is an interesting application.
No, what I meant was the technical difficulty.
Yeah. In the end, I wrote the algorithm. I designed the algorithm in a way such that it is a 2-time scale stochastic approximation. So the technical difficulties are going to be the same whether it's a multi-agent setup or a single agent.
So game is not bringing any technical difficulty as such.
No, that's because of the huge assumption of the strongly monotone gate. Yes.
So are there any assumptions in the convex sets which if you make, then these projections don't sort of destroy the property?
I don't have an answer on the top of my mind. I did spend significant amount of time trying to get a convex set where I do not have this problem, but I can briefly discuss what the reason is for getting the non-expansive mapping. Look at G of alpha. G of alpha is alpha plus AX star of alpha minus L star, right? If there is a projection, there is a possibility that for two alphas, alpha 1 and alpha 2, X star of alpha is the same. Which means that if I do G of alpha 1 minus G of alpha 2, what I get is alpha 1 minus alpha 2, and which makes it a non-expansive mapping. So as long as there is a possibility that two alphas give the same Nash equilibrium, this algorithm will have a non-expansive mapping. So yeah. Any other question?
This can be avoided if the boundary of the convex set is differentiable, no? The boundary of the convex set is differentiable, then this will not happen. No, it can still happen.
You know, the equivalent of the XR alpha itself,
Yeah.
multiple alpha
Yeah.
are going to some.
Okay, so let's go to the next scenario where we have a discrete choices of the parameters that the manager can choose from. So the manager has to choose from a discrete set of parameters, theta ranging from 1 to k. These can be thought of as different policies. Again, the objective is to maximize the global objective. Again, going back to the resource allocation game example, manager, for example, one setup could be manager is deciding which subset of the resources are available to which player, and it has k different allocations or k different configurations. A real life example of this would be the odd even rule, where odd numbered cars are allowed to use only the odd resources and the even numbered cars are allowed to use the even resource, for example. So that's the resource allocation setup. Manager chooses theta t, the players update their action using gradient descent. Here I am making two modifications from the previous algorithm. The step size is fixed just for simplicity, and I have removed the noise from this part. On the other hand, I have added a noise in the global reward that the manager observes. So the manager is observing some noisy version of the global reward at each time step. But what does it's important and it's a modeling choice, but it is important to formulate the objective of the manager. So the manager cares about the global objective at the Nash equilibrium. So the optimal policy is defined as the one which has the has the maximum global objective at the corresponding Nash equilibrium. The regret is also defined in terms of that. There could be other ways of defining the regret. For example, just in hindsight, what was the best action to take? Best policy to implement at each time. We define it this way. It's a modeling choice, but the intuition behind it is that we want the manager to choose an optimal policy and converge to it quickly, not switch between different policies again and again, which would make sense in a multi-agent setup because changing the policy at each time step is not desirable for the players.
So now with the time is coming into the picture, right? You wanted convergence.
Yes.
What is that scale and what is this little thing?
This T is the T of the T.
The discrete time slot.
Yeah, the time steps at which the players are updating their actions and the manager can choose to update its policy. This is the time scale. This is the time step.
Earlier outlook was that you first freeze the decision theta.
Yes.
Depending on theta, everybody converges.
But that wouldn't be an algorithm which can be implemented in practice because we don't know how long to wait, and it could be costly to wait as well because, for example, if some policy is significantly more suboptimal than the other, it implies that everyone has to sufficiently converge to that for that policy. So that algorithm won't work as such. So how is this different from scenario 1? In scenario 1, what the manager was doing was controlling a continuous parameter beta, and there was a possibility of slightly changing beta at each time step. Here there is no such possibility. It's a discrete set of parameters, and basically if the manager keeps changing the policy at every time step, they will learn nothing about the actual Nash equilibrium. They will just keep observing some oscillating version, for example. So, but again, we have the good part that if the policy was fixed for sufficiently large amount of time, it will get close to the actual Nash equilibrium. But the question is how long to wait and how to decide how to decide the appropriate time to switch between different policies. So that's where the good part of a strongly monotone function comes in, which is basically that exponential convergence. So if the policy at time t was theta, that means that the x at time t plus 1 is closer to the actual Nash equilibrium as compared to the actions at time t. This tau c is, we define this e power minus 1 by tau c so that it has some physical intuition and it shows up nicely in the regret expression, which I will show later. But it can be thought of as an approximate convergence time. This is the exact calculation for it. We don't need to go through it. So we model this problem as a modification of the standard stochastic multi-arm banded problem. In the standard multi-arm banded problem, the player or the manager chooses an action or an arm, and they get to see a noisy version of the reward for that arm. Here, the exact true reward cannot be known until and unless you wait for infinite amount of time. So we still solve this problem using an optimism-based algorithm. We modify the standard upper confidence bound UCB algorithm. We call it very nicely upper equilibrium confidence bound, which has three major differences from the UCB algorithm. So the major idea is how to get a bound on the global objective at Nash equilibrium. So recall the exponential convergence guarantee that we have. So the approach is we can use this to get a bound. Suppose consecutively for L time steps, action theta, policy theta was being implemented. That implies that e power minus L by tau c is the range between which the actual reward at actual global objective at the Nash equilibrium would be. And this is what would be our additional term in the upper confidence bound algorithms. But this in itself is meaningless unless the manager fixes a policy and implements it for a certain amount of time. So the next modification is an epoch-based system. Policies are not altered at every time step. Instead, they are altered at the end of every epoch, and the length of epochs keep increasing as the policy is chosen more and more. So the intuition is that promising policies are given more time to converge, and very easily, if policy theta has been chosen for m epochs till now, then the length of the next epoch will be e power m plus 1. So the length of the epoch is increasing exponentially. The third modification required is
You say the length of the interval is chosen depending on the policy. What the feedback you're getting doesn't tell you what the error bound is. So error bound is decreasing
yes.
with the length of this epoch. How are you dynamically adjusting it? Because the better the policy, you would expect to stay in that for a longer time. But that feedback you never get.
We do get it in some form, right? Because we do observe phi of xt plus L, which gives us a bound on phi of x star of theta.
Yes.
So we know that a policy is good enough, only then it received an opportunity to try itself for the m plus 1th time. So if a policy was not good enough, it would never have been tried for the m plus 1th time. I mean, it's noisy, so every policy will be tried sufficiently often, but in a noiseless setting, that's the idea. So the manager observes noisy rewards. It doesn't observe the true global objective. In a general stochastic multi-arm banded setting, what we do is we take the average of all the rewards till time t for that specific arm. Here we can't do that. We can't average all the rewards from an epoch. Why? If an epoch was of length L, the latter L by 2 are closer to the equilibrium, and hence they have more information. The first L by 2, they are farther from the equilibrium, hence less information. So we take a very simple approach. If the policy theta is implemented for L consecutive time steps, we average only the last L by 2. There can be many variations. We can do weighted average. You can ask why did we decide L by 2. All of these would only matter in the constant. They won't affect the actual regret in terms of T and tau C and so on. So this is a simple approach which works. So combining all of these, this is the upper equilibrium confidence bound algorithm. So the manager implements the policy theta n, which is the maximum of the UVCB theta at that time for an epoch whose length is defined based on the number of times that it has been chosen till now. The estimate is taken using the last ln by 2 rewards, averaging that, and the UVCB update, it has the standard estimate plus 2 terms. The first term, okay, sorry, let's look at the second term. The second term is what would be very usual for anyone who has looked at the UCB algorithm. So this is basically similar to the UCB algorithm with some variations coming because of the epoch structure. But the first term, this is the equilibrium bias, which dictates how far away we are from the equilibrium, and to get that much more optimism for that policy.
So shouldn't there be some difference on how many policies there are, because you want to have a decent upper confidence bond for all of them, or at least the top few.
Each, this with respect to each such option, theta is possibly one.
Yes, for every theta you have this.
Yes.
But this is like a probabilistic bound. This is a probabilistic bound on the value of theta.
Yeah.
Yeah.
That particular theta is the highest thing.
Yes, but for that to be correct, I would want to do some kind of a union bound or some epsilon type argument to say that, like,
That will come in the analysis.
That would come in the regret part, right?
yeah, but so what I am why so how is, so there's no depending on the number of arms at all.
If you included that, possibly you could have avoided the. Okay, I have removed the. Okay, the standard UCB algorithm also has no dependence on.
So yeah, sorry, that's what.
Yeah.
Not a put that. So how is that being avoided?
Maybe the speed of convergence will.
Oh, the speed of.
Yeah, it isn't being avoided.
Okay.
The algorithm is as such.
Huh.
In the regret, it will show up.
Okay, sure.
Yeah, it shows up.
Linearly.
Yeah, and linearly. Yeah. Which I have very conveniently not written here, but this is the expected regret. The first term, the standard log t by delta theta. This is the instant dependent bound, not the minimax bound. But log t by delta theta, where this is the suboptimality gap for the policy. We have two additional terms. This is a major one. But both of them have tau c dependence, linearly scales with tau c. We also show a lower bound, which is in some ways very intuitive. You can't beat the stochastic multi-arm banded lower bound. So the log t by delta theta is going to be there, but up to our bound is optimal up to log factors in tau c, and optimal up to constant factors in t and delta theta and k. So that's it. So what I discussed was game control under two different scenarios. One of them a continuous setup where the manager was changing the prices or the subsidies, and the algorithm there was a 2 time scale iteration method because continuously changing the actions was possible. Continuously changing the parameters was possible. The second scenario, a bunch of discrete parameters which the manager has to choose over, and here we naturally for a discrete parameter setup we gave an optimism based bandit algorithm. There can be many other scenarios. You can loosen the strongly monotone assumption, you can shift it to monotone, a slightly larger class of games where you don't have the like so nice properties. There could be many other applications. For example, for the equilibrium bandit setup, there is another interesting application of epidemic control where the government is trying to decide which policy is the best if a new epidemic comes up. So bunch of other possible scenarios as well. Thank you. And the talk was based on these two papers with slight mention of some 2 time scale works. Any questions on the setup scenario algorithm?
So this tau c, so there are some, so basically certain things are assumed to be contractive. Yeah, so this LG,
So LG is the Lipschitz constant for the gradient
so
operator.
mu eta should be bigger than LG square eta square. Something.
Yes. So eta needs to be sufficiently small.
Yeah, step size is
Yeah.
Is there a continuous time version of like this differential game that so there's 2 times scale thing, right?
Yes.
So if so there are so people that do this technique. I mean, okay, again, I don't know what you're talking about, but like so there are these differential games kind of thing, right? Where people that do a continuous time version of this, where like the policy might be changing continuously in time, and then so would there be some analog of 2 time scales there, or what?
I think there should be because I'm not sure about the noise part.
Yeah,
that would be,
noise.
if it's noiseless, I mean basically even the analysis for the 2 time scale setup, ignoring the finite time part, the convergence part is proven using the ODE approach for stochastic approximation. So it should be possible. Yeah.
So your controller objective function phi will be linear, I think.
In this case, it was linear. Yes, this was the basically.
How much more German can go?
So the first application that I talked about is actually a part of a larger studied problem known as GNEP, generalized Nash equilibrium problem, where instead of just converging to the Nash equilibrium, what we are doing is converging to the Nash equilibrium under certain constraints. So people have studied a whole bunch of things there, linear inequality constraints, linear equality as we did, non-linear inequality as well has been studied, but the rates vary, the type of algorithm varies. Some of them require, so this is like quite distributed in the sense only the Lagrangian multiplier needs to be transmitted. There are some where there needs to be much more communication as well. But yeah, GNEP is a standard problem which has been getting some focus in the recent years. This is just a application based control formulation of the same thing. Yes.
So could you show your final regret expression? So, I don't know the regress for the UCB gives, but if you take a large T, then both of them should match, right? Because the players should already have figured out where the equilibrium is, and then.
So, if I'm right, basically what you're saying is if T is like much larger than tau C,
Yes.
then this term wouldn't matter as much, which is right. Because basically log T is going to lead the thing, right? So this setting matters only when tau C is comparable to the horizon that you care about. Otherwise, I mean, you still need an algorithm for it. It's not like the UCB algorithm would work, but the regret would basically be dominated by the stochastic noise. And the equilibrium noise won't matter as much.
And the way you take averages for estimating the, if you do an exponential weighting kind of a thing, even that will only differ by a constant. Was it?
Yeah, because as I said, this term can't be improved. Because it's coming from the standard noise thing, right? And there are lower bounds for that set. And the tau C, even the tau C thing, we have showed a lower bound which says that this regret is optimal up to log factors in tau C. So yes, there is scope, but it's not a lot of.
Is that statement correct to say that you cannot improve the first term, even though you have so much structure that as tau C increases,
Yes.
you have a very bounded noise, which is exponentially going to zero.
But consider the case where tau C was. What would be the extreme case? Tau C is infinity, right? No, tau C is zero. Yeah. So this basically means that if you take one step, you directly know x star of theta. noisy, which is basically the UCB problem, which is basically the stochastic multi-bandage problem.
But that is true, but for sufficiently large towsing, where actually you're getting this contraction,
Hmm.
the rapid way. Is it fair to say that you cannot be using? Because.
But okay, intuitively, larger tau is going to make your problem harder.
If you get it smaller.
No, but
So what I'm
in-
saying is,
But in one case, I showed that this, okay, in one extreme, this problem maps to the standard stochastic multi-banded, which is the easiest version of the equilibrium banded. And the hardest version of equilibrium banded would be very slow convergence. And that should intuitively have a worse performance, right?
Any further question? Just thanks for that.
Yeah.